Hello, my name is Dylan Lewis, and I am the project lead for VALHALLA, the Venusian Atmospheric and Land Exploration, a human-assisted low-latency approach, which is a multi-level mission architecture for a crewed flyby of Venus by the Northeastern University Students for the Exploration and Development of Space. In this presentation, I will explain the mission's purpose and objectives, followed by a brief introduction to the mission architecture and project timeline. Then we will explore each system in more detail, discussing both the engineering design and science goals, and finally discuss the budget and future considerations for this project. When tasked with creating a mission architecture for a crewed flyby of Venus, we focused on a mission that not only satisfies all the criteria of this challenge, but necessitates the premise of this challenge, having a crewed flyby of Venus, and has robust reasons for visiting the planet. We have not had a dedicated mission to Venus since Magellan ended in 1994. Other space agencies have sent orbiters to the planet after 1994, but a crewed mission has never been attempted. Additionally, the most recent lander and balloon mission to explore Venus was Vega 2 in 1985. Recently, 2 new missions were announced, but while some of their scientific objectives overlap with ours, our mission will provide higher resolution images of the surface, more precise surface seismology and composition data, and prolonged in situ lower atmospheric data collection, among other things. Earth is experiencing climate change at an alarming rate. Understanding the atmospheric and geological history of Earth is vital to understanding climate change, but Earth is only one data point. Venus, our closest neighbor, is hypothesized to have been incredibly similar to Earth. Now it has a thick atmosphere of carbon dioxide, which traps the sun's heat. Understanding the evolution of Venus is crucial to understanding the effects of climate change on Earth. Long-term deep space exploration has yet to be attempted with humans. The prestige alone is reason enough to go to Venus, but having humans in this environment allows for research into the effects of long-duration deep space travel on the human body. By sending humans to Venus, we can demonstrate these technologies and conduct experiments as a testing ground for longer duration deep space missions, such as future Mars missions, any one of which will be nearly twice as long as a Venus flyby. These reasons guided our mission objectives shown below. To complete these objectives, VALHALLA will leverage the proximity of humans to teleoperate fixed-wing and quadcopter drones near the surface of Venus. Electronics and technology are not yet advanced enough and will not be advanced enough for these drones to operate autonomously. Thus, this mission is not possible without human crew. Starting at the top, the crew will travel in a commercial human-rated vehicle dubbed Odin, after the Norse god who reigns over Valhalla. Most of the mission will be dedicated to observing the effects of long-duration deep space travel on human health through various experiments and technology demonstrations on board Odin. To allow useful low-latency communications on the daylight side of Venus during the surface operation time window, the Satellite Information Forwarding, or SIF, CubeSat constellation is deployed by Thor, the cargo craft that will deliver both SIF and Freya to Venus. Freya, named after the Norse analog of Venus, is a Venusian high-altitude airship similar to the Havoc design, but modified to fit the needs of this mission. Its purpose is to conduct science operations in the lower atmosphere below the clouds and to deploy 2 types of surface drones. Drones are encased in an aerodynamic protective shell that quickly and safely drops the drone to the desired deployment altitude. Ravens, the information gatherers of Odin, are fixed-wing drones that will conduct reconnaissance imaging of the surface at higher resolutions than any orbiter has done before. The Wolf, Odin's other familiar in mythology, is a quadcopter drone that can carry and precisely place scientific equipment on the surface of Venus. Funding for this mission starts January 1st, 2025, with large investments into drastically raising TRL levels and developing testing facilities. Thor will launch in late 2030, and Odin will launch in 2032. Both spacecraft return in 2034. Johnson Space Center will serve as the mission co-lead, since this is a human mission, and JPL will be the other mission co-lead for the complex robotics needed.
Thor is a SpaceX Starship in the cargo configuration that will be used to transport Freya, the drones, and the SIF array to Venus. Starship was chosen because of its high payload capacity, low cost, and high probability of reaching TRL-9. Thor will also make use of SpaceX's orbital refueling technology before departing Earth orbit on a transfer to Venus, to allow for significantly more usable delta-V and payload. 1.2 years after its departure, Thor will arrive in a highly elliptical orbit around Venus and remain there for 2.5 years before returning to Earth. This orbit will have an apoapsis altitude of 97,000 kilometers and a periapsis altitude of 400 kilometers, with an inclination of 5 degrees, which corresponds to an orbital period of 1.5 days. 3 months before the crew arrives, Thor will deploy the Satellite Information Forwarding Constellation, or SIF, which consists of an array of 12 3U CubeSats. SIF will maintain constant low-latency coverage of Venus's equatorial regions, allowing for continuous communication with the surface.
14.5 days before the crew arrives within operational latency range, Freya will be deployed by Thor into the Venusian atmosphere. Freya is a non-rigid airship built for the planet's harsh environment and derived from the Havoc mission concept. Regarding its size, the design stands somewhere between the Phase 1 Havoc robotic design and the Phase 3 human airship, at 48.5 meters long and about 16 meters tall with a gondola included. Freya's main functions will be to conduct scientific experiments in the planet's lower atmosphere, as well as transport our surface scouting drones, the Ravens, and our heavier equipment-carrying quadcopter, the Wolf. Looking at the airship's balloon, we focused on two things: its drag coefficient and the maximization of the balloon's internal volume. With that in mind, the chosen shape was a medium nose paired with a medium fine tail and the fineness ratio of 3.6. This helps increase the drag coefficient, which in turn helps Freya slow down during the deployment phase, reducing some of the loads taken in by the parachute. It also has the best surface area to volume ratio out of the tested options of 3.6, 3.8, and 5. Although technically an even lower fineness ratio would mean a higher internal volume, it would also increase the mass of the outer envelope considerably, which should not be ideal for Freya to be able to travel at our desired altitude of about 41 kilometers while deploying the drones. Structurally, non-rigid airships are a lot simpler than semi-rigid and rigid ones. In a non-rigid airship, there are three main structural components in the balloon: a nose cone, load curtains, and an internal suspension system. The nose cone adds rigidity to the front of the balloon and prevents him from pushing in as Freya travels forward. It was designed based on what is commonly seen on Earth, with a larger solid component in front handling the higher forces and then battens helping the balloon sustain the wanted shape. The internal suspension system is contained in the balloon, attached to load curtains, and runs from the top of the envelope to the gondola in order to distribute loads throughout the whole balloon. Two other crucial components are included in the balloon design as well: the ballonets and the fins. Ballonets are added to the design to control pitch and altitude. They inflate to a maximum of 25% of the total internal volume of 4,920 cubic meters, each contributing half. The fins are located at the aft and help Freya stabilize as well as improve the whole system's structural integrity. Ideally, the fin layout would be two tail pairs in a cruciform formation, which increases both lateral and longitudinal stability while riding the high winds of Venus. However, due to mass constraints, the layout was changed to a classic inverted Y, therefore decreasing the total number of fins from 4 to 3 and cutting down on mass by about 250 kilograms. This is the same number of fins seen in Havoc. However, instead of going with a T layout as they do, we decided on the inverted Y because it has a higher stability and control. Shape-wise, the fins are trapezoidal, which simplifies the balloon folding process while Freya is being transported from Earth to Venus. For the materials, the balloon and ballonets will be made of Teflon, with the main balloon being 2 mm thick to prevent tearing and helium leakage, and the ballonets only 1.5 mm thick, since they won't be as exposed to the environment as much as the outer envelope. On Earth, airship balloons are usually 1 to 1.5 mm thick. Teflon was also the chosen balloon material in the Havoc paper, and it is currently only at TRL-3. All structural components, such as the fins, nose cones, and gondola, will be made of Dyneema, which is currently at about TRL-6, having been tested against sulfuric acid, showing little to no effect on its mechanical properties. Moving to the top of the balloon, you'll see the solar fabric. You'll be used to power all electrical components on Freya, such as the propulsion, scientific equipment, and deployment mechanism for the shells. At Freya's cruising altitude of 41 kilometers, and with a surface area of approximately 290 square meters, the solar fabric will collect almost 66 kilowatt hours. The Tesla batteries used for reference provide around 200 watt hours per kilogram. For Freya, 225 kilowatt hours will be provided through 3 of these batteries. But, as it is still a developing technology only at TRL2, it could possibly be substituted with other solar charging systems. Looking now at the gondola, the chosen shape was essentially a rectangle with rounded edges with a 1 degree inner taper from top to bottom. The bottom was then rounded out to improve airflow during flight. This maximizes the storage space needed for drone transport and deployment, while still giving the gondola some aerodynamic properties. On the sides of the gondola, you'll find our propulsion system. It was designed in order to keep mass down as much as possible, while not compromising on structural integrity. The full system, including the Tesla motors used as reference, comes in at 140 kilograms. For the propellers, a total of 4 blades was determined to be the best option to minimize mass, while increasing efficiency and structural soundness. Each blade has an airfoil cross-section, improving on its aerodynamic abilities as well as airflow properties. Internally, the gondola has 4 separate compartments. First, there is a pocket over the drone storage compartment where the batteries will be stored. Then the drone hangar, where 25 ravens and 1 wolf are transported in a honeycomb pattern. The dimensions of the hangar are enough to leave about 5 centimeters of space between each shell, therefore protecting them for contact with each other during transport and flight. In the future, the gondola size could be increased in order to accommodate a higher number of drones if necessary. Finally, there are 2 1-meter pockets, one on each end of the gondola, which will hold various types of scientific equipment.
The main atmospheric objective is to ascertain Venus's atmospheric composition, which is presently not very well understood. The gaps in our knowledge have led to misunderstandings, such as a 2020 study that claimed to have found a potential biomarker, phosphine, which was later unable to be confirmed. With a more thorough grasp on Venus's atmosphere, further research can be done on the planet's past and present. This will be accomplished by the first instrument on Freya, the Virtus Imaging Spectrometer. The second atmospheric objective is to study the circulation at different levels of the Venusian atmosphere. To accomplish this, the other instrument on Freya will be based on the temperature and winds for InSight instrument.
When designing our mission, it quickly became apparent we would need a method to deploy our drones from Freya to their operational altitude. Between the operating altitudes of Freya and the drones, the Venusian atmosphere holds clouds of sulfuric acid that would likely corrode and greatly reduce the functioning time of each drone. Our solution to this problem involves encasing each drone in a protective, aerodynamic shell that not only reduces drone exposure to the atmospheric surroundings, but also allows for greater control of descent and deployment speeds. These protective shells are housed in Freya's drone bay. Most shells are attached to Freya with 2 points of contact. The first of which is a pyrotechnic fastener that connects the upper section of the shell to the ceiling of the drone bay. The second is a dish covering that seals the opening the shell falls through during deployment. This dish is intended to provide stability to the shells while not being deployed. Once a shell reaches the target altitude between 500 and 1,000 meters, the upper section, or tail cap, separates from the main body to allow for the deployment of a parachute. This parachute will slow the shell to the deployment speed of 10 meters per second before the lower section, or nose cone, detaches. The drone is then released from the shell, and its wings are allowed to deploy. A similar process is done for the Wolf. We anticipate this process from Freya to full drone deployment to take just under 14 minutes for the Ravens and 20 minutes for the Wolf.
The first type of drone Freya will carry is the Raven. The Ravens are lightweight analog drones that are teleoperated by the crew on board Odin. Their primary purpose is to perform high-resolution reconnaissance imaging close to the surface of Venus. They will also provide in-situ measurements of the temperature and pressure conditions on Venus. The Ravens are designed to operate within a few hundred meters of the average surface level. They must withstand high temperatures and pressures, along with flying in a dense atmosphere. We considered 2 high-level designs for the Ravens. The first was a hybrid drone that could both glide and hover. However, we decided to pursue the current design in order to reduce power consumption while maintaining all reconnaissance capabilities. This current design also features a folding wing to minimize space while stored on Freya. And once launched, the wing unfolds and locks permanently. For the Raven airfoil design, the NACA 653-618 airfoil was selected for its high lift to drag coefficient ratio at 0-degree angle of attack and at the large Reynolds number experienced due to high air density. The airfoil also has the benefit of a large stall angle. The wing has a large aspect ratio to reduce the induced drag, similar to gliders. The wing area was estimated with the Ravens moving at a speed of 10 meters per second. Next, we went with a conventional aft tail configuration to minimize size and weight for storage on Freya. The horizontal and vertical tail sizes were estimated based on the length of the body, which was dictated by the payload. We also considered tail options such as the V-tail to reduce the space taken up by the vertical tail. However, the V-tail does not maintain stability as well as the conventional configuration. The propeller diameter was calculated based on parasitic and induced drag calculations, with a safety factor of 1.25. This propeller diameter was selected to minimize motor power consumption to 356 watts. With other electronics and onboard batteries providing 607 watt-hours, the Ravens are able to fly in the best case for 1.65 hours, covering a distance of 59 kilometers. We've also selected a space-rated brushless DC motor from Avior Control Technologies. Lastly, inside of the Ravens, there are 3 cameras, which are used to capture images of the surface for science and navigational purposes. The wing folding mechanism is actuated by a set of torsion springs, which allows the mechanism to be inside the body of the Ravens.
The Ravens will focus on photographing the surface of Venus. The imaging window of each of the cameras will be set to a different wavelength to obtain data in the low infrared, red, and green parts of the spectrum. These wavelengths will help identify some of the composition of the surface. The Ravens will observe the volcano Mont Mons and the Alta region, which has evidence of lava flows. The mission will also allow for a Raven to be sent out to find one of the Venera probes to analyze how the Venusian environment has changed them over time. The photographs that the Ravens obtain will support the objective of obtaining data for the development of future machine learning algorithms for autonomous missions to the Venusian surface.
The second type of drone is the Wolf. Building off the research and principles of the Ravens, the Wolf is designed to safely and quickly descend to the surface of Venus to place scientific equipment based on the initial exploration performed by the Ravens. The Wolf is constructed from a silicon carbide matrix composite, which the Ravens also use due to its ability to withstand corrosion, high temperatures, as well as contain a high strength-to-weight ratio to combat Venusian pressures and carry a low mass flight. Using the same material for both helps to reduce mission complexity while also fulfilling all necessities of the craft. The primary difference of the Wolf is its quadcopter structure, as the glider-based design of the Raven is exchanged for a more traditional drone to specialize for landing. The drone is centered by a spherical body, allowing for exploration with minimized drag. The Wolf also features 4 landing legs based on the design of the Mars Ingenuity helicopter to allow for a safe touchdown. The Wolf will require an umbilical cord to power the scientific instrument using the Wolf battery, a concept based on the Mars InSight mission. The Wolf contains 2 cameras for navigation and science purposes. Scientific instruments attached to the crossbar underneath the Wolf, providing flexibility and modularity of surface science instruments.
The instrument payload of the Wolf will be a seismometer for the purpose of studying volcanism and seismology on Venus. The seismometer will be based on the design of the Keck Institute for Space Studies Pathfinder Surface Seismology platform, and would be able to obtain information on seismic backgrounds in the 1 to 5 Hz and 0.01 to 1 Hz ranges, as well as temperature, pressure, and wind speed data to reduce errors in seismic measurements. The experiment would focus on verifying the existence of seismic activity on Venus and obtaining information about the seismic background that future studies would have to contend with. Because of the length of the seismometer's lifetime and the lack of data on Venus's seismic background, we have chosen Mont Mons, a site with predicted seismic and volcanic activity, as the location for seismic measurement to optimize data collection. Due to size and mass constraints of the current design of Freya and the Wolves, only a single Wolf can fit into Freya's gondola. However, a mass redesign would allow for at least 2 to be used on the Valhalla mission. The purpose of the second Wolf would be to ascertain subsurface composition, and its scientific payload would be an ultrasonic drill and a mass spectrograph. And the samples analyzed would be from one of the regional plains, which make up roughly 60% of Venus's surface. The drill would use ultrasonic coring technology to collect 15 grams of sample, and this process would take approximately an hour, allowing for multiple samples to be analyzed.
The imaging systems on the Wolf and Ravens were modeled after the Venera missions. Each camera is a Vidicon-based analog camera designed to transmit a standard NTSC signal. The cameras are designed to use modernized analog circuitry to minimize the use of silicon while allowing operations at temperatures above 200 degrees Celsius. On the Ravens, each camera feed will be cycled per frame to achieve a maximum frame rate of 10 frames per second per camera. One of two active Ravens will transmit at 800 and the other at 806 MHz. The Wolf will have each camera transmit at 30 frames per second on separate frequencies. The ultra-high frequency band was chosen for communication between the drones and SIF based off of assumptions of Venus's atmospheric absorption window, and the K above band was chosen between SIF and Odin for higher bandwidth communications. Each transmitting camera will additionally be able to carry sensor data in two methods. The unused audio carrier can carry large amounts of analog data, while Line 21 encoding can carry up to 480 bits per second of digital sensor data.
Advances in high-temperature electronics will be crucial for this mission. Currently, silicon carbide integrated chips are very promising and are TRL-5 for Venusian purposes. A lithium ferrous sulfide molten salt-based battery serves as the main battery for these drones, which has been prototyped and tested at 500 degrees Celsius. TRL-9 high-temperature electronics and components are not yet at the desired temperature range, but continued development over the coming decade will bring them to what we need.
Surface operations begin when Odin is within the 20-second round-trip latency zone through communications via the SIS constellation. Over the next several days, latency will continue to drop, allowing for more direct control over the drones. On April 17th, Odin will enter direct line-of-sight communication with the drones, vastly improving the latency, and will deploy the Wolf at that time. This time should correspond to Freya's location being near or directly over the Matmons region so as to collect seismic data. Raven will be deployed a few minutes before the Wolf to aid in finding a safe and optimal landing location.
The human component of the mission will launch on a human-rated SpaceX Starship dubbed Odin. Similar to Thor, Odin will refuel in low Earth orbit before departing to Venus on a trajectory designed to minimize travel time and delta V. Odin will make its closest approach on April 17, 2033, with an altitude of 0.77 Venus radii, or 4,660 kilometers. Odin will then return to Earth and arrive on January 14, 2034, 384 days after departure, where it will undergo aerobraking maneuvers to return the crew safely to the ground.
The largest cost savings from the mission comes from leasing a human-rated habitation vehicle from a commercial company instead of developing one from scratch. A SpaceX Starship was chosen for Odin because it's the cheapest option, the most adaptable for the mission, and has the highest probability of reaching TRL-9 by the time the mission starts. Odin will transport the crew of 4 scientists to Venus and back, and will require a few modifications to add needed extras equipment for crew health and communications equipment for drone operations.
VALHALLA will function as a testing ground for crewed long-duration deep space missions, and will thus be a precursor to potential missions to Mars. The health of the astronauts' musculoskeletal, nervous, and cardiovascular systems will be monitored throughout the mission to determine the impacts of long-term space travel. An experiment to determine the sufficient amount of exercise needed to maintain health in space will be conducted. The crew will also receive personal radiation dosimeters to track their exposure to radiation. The VALHALLA mission will require a variety of scientific instruments to monitor human health. These instruments include a Holter monitor to measure heart rate, an ActiWatch to measure movement, and a continuous blood pressure device. VALHALLA will also utilize a bioanalyzer developed by the Canadian Space Agency to test the astronauts' bodily fluids, such as blood, saliva, and urine, for biological signs of stressors. In order to help mitigate the effects of weightlessness, leg cuffs and a short-arm human centrifuge will be utilized. The leg cuffs will increase pressure on the lower sections of the body in order to prevent major increases of blood flow to the brain and intracranial pressure. The centrifuge will be used to reduce blood pressure and bone density loss and increase heart rate. Each astronaut will spend 30 minutes of the day in the centrifuge set to create the same effect as standing on Earth. The ISS Benefits for Humanity report indicates that the current exercise regimen is insufficient to counteract the negative effects of weightlessness. Thus, the VALHALLA program will increase the duration of the exercise regimen to 3 hours per day while maintaining the same intensity of the workout. Exercise equipment will include the combined operational load-bearing external resistance treadmill, as well as stationary bicycles. The crew members will follow identical schedules staggered by intervals of 6 hours. This allows one astronaut to be awake and working at all times, which is necessary for the Valhalla concept. The staggered schedule ensures that the crew members do not need to alter their circadian rhythms over the course of the mission. Since the crew will be operating on different sleeping schedules, the risk of negative effects as a result of isolation will be present. To mitigate these possible effects, the schedule is designed for crew members to work and eat together as much as possible. Before the launch, the crew will also participate in numerous team bonding sessions in order to foster a connected and supportive environment.
The budget for this flagship mission is based on estimates from the Advanced Missions Cost Model and from analogs such as Ingenuity and known and projected launch costs. Valhalla has a total budget of $15.71 billion fiscal year 21, which puts the mission at an average cost of under $2 billion per year from start to finish. Included in this budget are two $1 billion Starship leases, which are possibly overestimates, funds to raise TRL levels, and funds to build a Venusian atmospheric test environment large enough for the Ravens, Wolves, and a scale model of Freya. Item numbers include prototypes, test models, and final models. Valhalla benefits from having similar subsystems such as the Ravens and Wolves, which are built on related technologies and can be developed in parallel, which helps lower their cost. In future design iterations, we plan to increase the size of Freya and the gondola to accommodate at least one more Wolf. Further reductions in mass and size can be made for the drones. The camera size is the largest limiting factor for drone size and needs to be reduced. More passive heat shielding and more battery capacity will increase the longevity of the drones to reach the original goal of 3 hours of operation. We have presented a robust and comprehensive mission architecture to effectively capture the condition of the Venusian atmosphere and surface along with the effects of long-term space travel on the human body. The combination of the Ravens for reconnaissance and the Wolves for heavy instruments will provide a thorough exploration of the Venusian surface, which will deepen our understanding of the solar system and our own planet. Through the recording of human health data, ranging from physiological to mental health, we will gain insight into the data strategies and methods for maintaining crew members on future long-term space missions. As the first long-duration crewed deep space mission, Valhalla's mission architecture will provide a major leap forward in interplanetary travel and will be a stepping stone for future missions to Mars and other bodies. The technology needed to execute this mission is not yet fully realized, but with time and funding, it can be. In doing so, humanity can take the necessary steps to continue to learn, explore, and chase curiosity. This concludes our video presentation. Thank you very much for your time and attention.